So that's what I know about stromatolites. And obviously, in the process of checking the chat window, I've caused everything to crash. But any questions?
No.
All right. So unit 4, gravity in orbits, tides, resonance. Should be an easy unit. I don't know if that's how it'll turn out. So, as I'm sure you've noticed, I asked the same kind of questions over and over and over again. Now y'all have done enough homework and been through enough units, I can give you the first quiz. But I refuse to give you the first quiz until I'm caught up with grading. So that's not happening yet. Let's get ready for it. Challenge problem. 6 hours later, which of these constellations will be highest and why? Write your answer and then show me. Is it 1, Aquarius, 2, Capricornus, 3, Sagittarius, 4, Scorpius, or 5, Libra? So in order to help you, I want to remind you that 24 divided by 6 is 4. And also think about which way the stars turn when you're facing south. Thus far, I've only gotten one answer. Looking for more than that. This is one thing out of many things I absolutely want this class to understand. So even if you're wrong, give it a try. Oh boy, it's a quarter a turn of the sky. So imagine the sky turning by 1/4. I'm not asking you which of these is actually right. I'm asking you which is closest. If you're looking north, the stars turn counterclockwise. If you're looking south, the stars turn clockwise. All right, this is something we have to go over. I guarantee you it will be on the first quiz because I've already written the first quiz. And the moment I get done with all my grading, I'm going to assign it. If you wait 12 hours, that's half a turn in the sky. 6 hours is a quarter turn in the sky. Meaning for a 12-hour period, the sky would turn a whole half turn. Every star in that picture that was above the horizon would be below it. For a 6-hour period, the sky turns a quarter of a turn. This is for the northern looking perspective. Oh, no, it's not. That's for the northern looking perspective. And that's for the southern looking perspective. So if you've got constellation A, constellation B, constellation C, constellation D, and constellation E, and you're looking to the south, then 1/4 of the turn of the Earth later, this one is going to be the highest. So I'm going to have to go back to the original screen to see what the right answer is. But I believe that was Aquarius. Let's go check it out. Yep, it was Aquarius. So a more proper and formal answer is that whatever sign of the zodiac is before Aquarius, it'd probably be the highest, since Aquarius is already a little bit above the horizon. But that wasn't really an option. And I also have no idea what sign is before Aquarius when it's Aquarius Capricornus. So even if you gave me the right answer, I wouldn't know. Just not that into astrology. So the answer is 1. And I really need you to understand this because your points in the class are going to depend upon it. And not from this graphic either, from some other graphic. So, questions, especially from those who didn't necessarily get the right answer. All right, well, somebody told me I explained it perfectly, but I also got a whole bunch of answers that I did not consider to be the most correct. I'm also open to being wrong if anybody wants to tell me why the answer is something else. It wouldn't be the first time I got something wrong, that's for sure.
Just to clarify, you said that the northern hemisphere goes clockwise or counterclockwise, and the southern hemisphere goes counterclockwise?
The northern hemisphere goes counterclockwise, the southern hemisphere goes clockwise. This is something I have a persistent problem with. I don't like it, but it happens to be true. And you can convince yourself of this by remembering that everything rises in the east and sets in the west. So think about what the stars look like if you were looking south, and then think about what the stars look like if you were looking north. Other questions, follow-up questions, because this is definitely going to be some percentage of your grade. The same way that moon phases will be some percentage of your grade. All right, I just counted to 5 in my head. So I gave you a whole bunch of gossip about Tycho Brahe and Johannes Kepler. Just remind yourselves, Brahe had excellent eyes and was a jerk. Kepler was extremely sickly and had terrible eyes, but was very good at math. And Kepler was the person who actually unlocked the 3 rules that planetary motion follows. And not just planetary motion, this is also how moons of planets behave. He could not, however, say why. Newton's theory of gravity combined the laws of motion with Kepler's laws and planetary orbits. Of course, nowadays we say Newton's theory of gravity, he would have said the Holy Spirit force. Gravity is a kind of force. A force can be a push, a force can be a pull. That's what forces are. There's 2 different main types of forces. There's the forces that occur when 2 objects physically touch and one pushes or pulls on the other. So a quick example of that. Whoosh. Whoosh. Push or pull. But long-range forces is when an object can feel a push or a pull from another object without touching the other object. Quick example of that. Another example, in case I went by too fast for the camera to catch it. The Earth is not touching the whiteboard marker, and yet it has an effect on it. So this is far beyond the reach of this class, but you may be wondering how on earth this kind of thing happens. And the answer is that there's particles called mediation particles that move in between objects. For light, they're called virtual photons. For gravity, they're called gravitons. We still haven't found gravitons. We have found gravitational waves, but not gravitons. But this is a basic idea. Something with mass could throw a kind of basketball called a graviton at another piece of mass. And when that other piece of mass catches the graviton, it's pulled towards the object. It's the exact opposite of the way a basketball works when you toss it to somebody. And for electromagnetism, which you're probably most familiar with from magnets. The virtual photon that is exchanged can either push an object away, just like a basketball would, or, in the case of different charges, it can pull it towards, just like gravity does. So all that is weird and not anything you want to worry about in terms of passing this class. I just thought I'd pass the information along And now we are done with the extent of my knowledge of quantum chromodynamics. In SI units, we call force newtons. In imperial units, it's called a pound. It's in the unit you weigh when you step on a scale. The force of 1 Newton is about the weight of one large apple in Earth's gravity, incidentally. So I weigh, unfortunately, about 980 newtons. So it would take 980 apples to equate the weight that I exert on the ground. So when you consider forces, you got to ask the question, who or what is applying the force? In what direction does the force point? And is this a contact force or a long-range force? This person is exerting a contact force. The more force she exerts, the greater the acceleration. Acceleration is not velocity. It is not speed. It is a thing that changes velocity or changes speed. Is your gas pedal or your brake pedal, not your speedometer. So a lot of force is equivalent to stepping on the gas pedal really hard, or stepping on the brake pedal really hard. So the box is originally sitting still. The woman applies the force on the box to the right, and thus the box begins to accelerate to the right. If she can keep up with it, it's going to have a greater velocity every single second. This is an example of a long-range force. So some pitcher throws a ball. At the very beginning, they apply a contact force on the ball, throwing it up and to the right. But the long-range force of gravity acts on the ball at every single given instant. And it changes the direction of travel, and it changes the velocity, so that all of the upwards velocity gets eaten away, and then eventually gets transferred into downwards velocity. Newton's second law of motion. If a force acts on an object, it will cause the object of motion to change. The object will accelerate. Acceleration is a change in the object's speed, either faster or slower, and or a change in the object's direction. So this is important for astronomy for this reason. Let's imagine a completely circular orbit. Here's my poor approximation of a circular orbit. Let me pin the whiteboard real quick. Is everybody seeing the whiteboard as being big?
No.
No. Okay. Back to the drawing board. How about now?
Yep.
Great. So, as you know from last week, if an orbit's an all elliptical, an object is going to move faster when it's closer to the sun than when it's further away from the sun. But if the orbit is perfectly circular, then it moves at the same speed all the time. But is it accelerating? And as it turns out, the answer is yeah, it is. There was an inward force pointing towards the sun at each of these points. And that corresponds to an acceleration. This is not a physics class, so I'm not going to delve into this with too much depth. But velocity is a measure of not only how fast you're going, but what direction you're going. If the direction that you're going is constantly changing, then you are being accelerated. Quick example of this, you feel forces when your car turns. They're pseudo forces, but they're forces nonetheless. So drive at speed, take a hard right or left turn in a safe place, and you'll feel yourself pushed either towards the door or away from the door. That's a clue that you're being accelerated. And also, each and every one of these velocities is pointing in a different direction. That means there was an acceleration. The velocity is changing. So contact forces and long-range forces, of which the only two you really experience are gravity and electrostatic. There's two other forms of forces. One of them is called the strong nuclear force, and one of them is called the weak nuclear force. And both of these are, hold on, I'm gonna text my dad. And both of these are forces that can change the velocity of an object by applying an acceleration. And all accelerations imply the presence of a force. Things only change velocity when a force is applied to them. Gravity is a mutually attractive, long-range force between two objects with mass. It's a fundamental force of nature. There's only four: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Due to the nature of astronomy, we're actually going to get into the strong nuclear force and the weak nuclear force eventually, which is in stark contrast to what would happen in a physics class where we just stay far away from them because the math needed to describe them is far too difficult. Since this class doesn't involve math, we can dip into them. As far as gravity goes, the more mass the objects have, the more strongly they are attracted to each other. So very massive objects can exert very large forces on each other. This attraction is expressed as an acceleration. The objects will change their speed and direction so they can become closer together. They're attracted. Imagine that you walk to the top of this building. Imagine we're all in the same building for that matter. with a 5 kilogram bowling ball, a 1 kilogram hollow rubber ball, and a 1 kilogram large square piece of cardboard. Both balls are the same size and shape, but one is lighter, of course. The cardboard is the same weight as the hollow rubber ball. You drop all 3 objects from the top of the building at the same time. Which object will hit the ground first? Private or public message me your answer. The nature of the answers that you're sending me makes me think that your high school physics teachers were remiss in having y'all do an experiment where you built a little parachute for an egg and dropped it off the top of the building to discover where the egg fell. So, eggs have a very large surface area. Parachutes have a much larger surface area. And drag forces are real. So, when you attach a parachute to an egg, it falls more slowly. Cardboard itself has a very large surface area relative to its mass, so it too is going to fall more slowly. The air is there. We haven't eliminated it. It exists. So the answer that's in the notes is that both balls hit the ground at the same time and land before the cardboard. I will absolutely forgive anybody who says the bowling ball will land first because you're formally right. Like both the bowling ball and the rubber ball experience some amount of drag, but it's pretty hard to measure for 2 relatively compact spherical objects. But the cardboard's definitely not hitting first. It's going to flutter, just like a feather does. It doesn't make sense. I just counted to 5, so I'm moving on. So, the gravitational force of Earth causes all objects on the surface to accelerate downwards towards the center of the Earth at the rate of about 9.8 meters per second squared. That means if we subtract away air resistance, well, first off, let me change the number 9.8 to 10, because I don't really want to do math. So, after the first second, an object will be falling at 10 meters per second. After the second second, an object will be falling at 20 meters per second. After the third second, it will be falling at 30 meters per second. After the fourth second, it will be falling at 40 meters per second. This constant downward acceleration was observed by Galileo in the early 1600s and holds true no matter what the size, shape, and the mass of the object is, as long as we're not worried about air resistance. But we really should be, because that's a real thing in Earth's atmosphere. Even when you're just skydiving, you can feel it. If you curl yourself into a ball, you'll fall faster than if you spread your legs and your arms and you turn your body towards the direction that you're falling. If you're wearing one of those skin suits, you can even have more of an effect than that. Let's look at some proof of this. And here, of course, proof is in quotes. I present to you the movie stadium in LA where they faked the moon landings.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his findings.
So in case it's not obvious, I'm being facetious/sarcastic. I don't think the moon landings are actually faked. I'm just a big admirer of the movie Hackers.
Isaac Newton.
You also see my YouTube? I'm not sure if I lost audio yet again.
We're still here.
But are you seeing the YouTube?
Now we are.
Okay.
That's just brilliant. One, release.
Here's a bowling ball and a feather falling inside of a vacuum chamber. And I think we all instinctively know that in air, a feather will not fall at the same rate as a bowling ball.
Look at that.
So yeah, in the absence of air resistance, things fall towards the Earth at the exact same rate. But air resistance does have a substantial effect. And finally, Newton's first law. An object in motion tends to stay in motion. An object at rest tends to stay at rest unless acted upon by an external force. One problem that is relevant to astronomy and plays into this question is what happens to the motion of planets or moons when the object they're orbiting suddenly vanishes. I'm going to draw 5 different potential paths on the board. Pick the one that you think the planet would journey on if its star were to vanish suddenly. Seeing the chalkboard?
Yes.
Great. Here's Sol. Here's Earth. Earth has been going around Sol that away, assuming that away is counterclockwise. Sometimes I get it confused. And then the sun suddenly vanishes. So does Earth go that away, that away, that away, that away, or that away? What say you? Let me know on the chat screen. Ooh, I'm getting a whole bunch of 4s. Everybody's saying 4. So I guess everybody will say 4 after this point. You're not wrong. They will continue in a straight line. And let me share with you a little bit of weirdness, an odd fact. barring human interference, life on Earth would last longer if our sun suddenly ceased to exist than it will if our sun continues to exist and do its regular thing. This is because, in the absence of solar heating, the Earth's core is still hot. So the oceans freeze over, they cover almost all the land mass. At the very, very bottom of the ocean, we still have geothermal energy emerging, and it will for billions of years. And so life can cling to those geothermal vents and continue to exist. Now, if we stay in orbit around the sun is on schedule to evaporate all the water on this planet within about 500 million years. To put this in perspective, if we can beat global warming, that's like a warm-up, pardon the pun, for dealing with what the sun's about to do. There's no reason why humans can't cope with this problem as long as our civilization doesn't collapse. But if we don't do anything, if no intelligent life on Earth does anything, then all life on Earth dies within 500 million years. Whereas if the sun were to vanish, it would take us another 3 billion years or so for all life to perish. Granted, the life that exists in this circumstance would not be particularly interesting to us. We're talking about tiny little organisms that are hanging around thermal vents, but still, curious that life on Earth would exist for longer without the sun than with it, barring intelligent interference. Newton's second law of motion. We've already talked about this, but let's talk about it more. Oh, hold on. Someone's got a question in chat. Plus, we can factor in the eventual explosion of the sun leading to our Earth's extinction. So the sun's not so much going to explode, it's more going to slowly outgas. We'll talk a lot more about that a little later. But yeah, the sun will eventually do that thing. It'll either fry Earth or won't. But that's 5 billion years from now. A mere 0.5 billion years from now, the sun's going to get hot enough that it's going to evaporate all our water. No water, no life. At least not as it's evolved on Earth. So the sun's got our number well before it gets to the red giant stage. Oh, great. Okay, so back to Newton's second law. Force is equal to mass times acceleration. Or acceleration is equal to force divided by mass. So let's imagine that you come around and you hit a little rubber ball. Then imagine that you come around and you hit a semi-truck. Which of those two objects experiences more of an acceleration? I'm guessing you're going to pick the rubber ball because it's got far less mass. You're exerting the same force against both objects, give or take. Probably more against the semi-truck, honestly, because it's not going to move as you're hitting it. But that really doesn't matter because the mass of the semi-truck is so huge that it's really not going to accelerate at all. In circumstances around Earth, acceleration is, due to gravity, always 9.8 meters per second squared. Sometimes a little less, climb Mount Everest and you might get 9.78, but it's pretty much always the same. Up around where the International Space Station is, I think it's 9.6. So they definitely haven't escaped Earth's gravity, and if they had, they wouldn't be in orbit. Gravity is required for orbiting, after all. So, if you replace the A with a G, what does force really mean in the context you're most familiar with? And the answer is weight. Force of gravity on an object is known as weight. And so, how much you weigh is really dependent upon how much the planet that you're standing on is pulling on you. If you go to the moon, your effective weight is going to be 1/6 of what it is on Earth. That's why you see videos of those astronauts bounding so high, which, if they were doing this at a soundstage in LA, would require the use of strings. But I think they probably landed on the moon and were just jumping in a low gravitational environment. Feel free to disagree. You can't lose any points for any sort of religious beliefs. Newton's third law of motion. Whenever you push on something, it pushes back with equal strength in the opposite direction. For every action, there is an equal and opposite reaction. So, one of the consequences of this is that I'm exerting 980 newtons on the Earth, and the Earth is exerting 980 newtons on me. I'm pulling on it in an infinitesimally small fashion, but it still is real, and it still counts. Which leads to that old question. If everybody on Earth all gathered on the same side of the planet, and they all jumped at once, what would happen? And the answer is nothing. By way of example, let me put it this way. If the Earth was the size of a basketball, which this is not in real life, but I'm holding it close, so maybe it seems to be, and you were to rub your fingers around it, the basketball would feel imperceptibly damp. Like you'd think maybe there's a little bit of water on it. That would be all of the Earth's oceans. Given that every ocean on the planet would make the Earth feel just a little bit damp if you were to be touching it, what difference would every human make if they all gathered on this spot and they all jumped at once? Sadly, or happily, none. So, Newton's third law is important in a couple ways to astronomy. One of the ways that we're going to consider gravitational force pairs and how those work. There's also how rockets work. So I'm going to show you two different videos and then explain how rockets work to you and how that relates to Newton's third law.
to orbiter internal power at this time. Discovery is now running off its.
I don't expect you all to share the same sensation as me, but this always gives me chills. But I grew up in the era of Challenger exploding and the space shuttle being an actual thing.
And we have a go for auto sequence start. Discovery's onboard computers have primary control of all the vehicle's critical functions. T-minus 17 seconds and counting. 15, 12, 11, 10, 9, start, 2, 1, boost ignition, and liftoff of the transmitter Discovery returning to the space station staging point.
So, planes can't fly without atmosphere. Helicopters can't fly without atmosphere. As a matter of fact, helicopters are so limited that if they try to land on Mount Everest, it's difficult for them because there's not enough air for their propeller blades to push against. Rockets don't have this problem. The space shuttle doesn't have this problem. It can work literally without any air around it whatsoever. How? Here's how. Let's go back to the original video. The way a rocket works is really not all that different from the way a machine gun works. You can easily imagine the space shuttle is basically just firing a ton of super tiny bullets downwards. None of them have very much mass, but they all have a lot of velocity. And consequently, due to the reaction pairs of forces, the space shuttle starts to lift up. If ammunition weren't a problem, and you're falling from a great height, you could point an automatic weapon at the ground and fire it until you basically weren't moving and descend to ground very slowly. Now, I'm someone who knows very little about guns, or more accurately, I'm somebody who cares very little about guns. But I do have to note that only one gun, as far as I'm aware, can fire in outer space, or only one mass-produced gun, and that's the M16. Because bullets in the M16 contain their own oxygen for firing, That's also why they can fire underground and in the water and so on and so forth. Certainly an AK-47 and a Smith & Wesson don't. So that's how rockets work. They spew out a ton of super tiny particles at very high velocity, and that makes the rocket go the other way. Challenge problem. A big challenge problem. Another one I can promise you a quiz will address in some way, shape, or form. The picture below shows a person in Napa pointing at the sun, which is currently in the constellation Scorpius. 12 hours later, half a day later, one half of the turn of the Earth later, what constellation will the sun be in? Write down your answer. And of course, we aren't going to do a discussion with your neighbor because we have no neighbors anymore. But still, please chat me what your answer is. Don't worry about your spelling. Person who private messaged me. My spelling is also atrocious. I'm getting a wide range of answers. And yet I've only heard from 3 students. Let's hear from the rest of you. I will zoom back into the slide. There you go. Keep on giving me answers. I'm just drawing something. Okay. Here's the Earth. Here's the sun. Let me redraw this so it's better. Great. 12 signs of the zodiac. or as the International Astronomical Union would have you believe it, there's 13 now. If the sun is blocking that constellation, the Earth turns half a turn, but it only moves by one of 365-ish of its total orbit. So if it's blocking that constellation one day, if the sun is blocking that constellation one day, it's going to be blocking it the next day as well. So if Scorpius is blocked by the sun, Scorpius is still blocked by the sun. Your birth sign doesn't change every 12 hours. It changes every month. Because what determines what sign you're born under is which of the zodiac constellations is blocked by the sun on the day you were born. This is something I consider to be really important to the understanding of astronomy because it links directly to astrology, which is, let's be honest, probably the thing y'all are closer to. So, questions / does it make sense? Do y'all now understand, well, Scorpius is the constellation that is in the zodiac blocked by the sun, both when you're pointing to it and 12 hours later when the Earth has undergone a full half turn. Why didn't it apply to the first challenge problem? I'm going to go back to the first challenge problem, just because I don't know what it was. Okay, so that must be it. In the first challenge problem, we're dealing with how the constellations change as the Earth rotates. Now, if I had told you that the sun is blocking Sagittarius or Aquarius and asked you which constellation is the sun with 12 hours later, the answer would still be Aquarius. The sun would have changed from rising to setting, but it would still be associated with the group of stars that it was associated with at the start of the day. Does that help? Further questions? All right, I'm moving on, but this is a big point. I'm gonna get at it with some quiz at some point in the future. So if it doesn't make sense now, shoot me a message. We can set up a private Zoom meeting or stop by and visit me before class or something like that. This is a topic I definitely want you to understand. So, what characteristics about two objects does the force of gravity depend on? Well, there's...
Wait, I have a question.
Yes, please.
What was the answer for the last thing we were just talking about?
It's still in Scorpius. Let me go back to the whiteboard. If I can. Are you all seeing the whiteboard?
Yes.
Great. So let's say this is Scorpius. I don't know if I spelled it right, but fortunately I don't care. Anyway, that one's Scorpius. So what it means for zodiac sign to be present in terms of your astrology prediction is that the sun is blocking that constellation. 12 hours later, the Earth will have spun one half of the time, but it's only going to move along its orbital path by 365 times 2 is 780. Somebody check my math. Nope, that's definitely not right. 730?
That's correct.
Okay, so it's moved along its orbital path by 1 over 730. So it's moved just a minuscule amount. The sun is still blocking Scorpius from the point of view of the Earth. Like, it's going to take a month for us to move to the point where the sun is blocking another constellation of the zodiac.
That actually makes a lot of sense.
Great. I'm so glad to hear it. That is literally what my job is. Please interrupt me and ask questions anytime you feel like it. Otherwise, especially in a distance learning environment, all this is completely pointless. So, mass of the Earth, mass of the apple. The difference between the Earth and the apple are the things that determine what the force of gravity is. Hold on, new chat message coming in. Can I explain the great attractor as a supermassive black hole? No, it isn't. All right. Well, you all seeing the whiteboard again?
Mm-hmm.
Great. The Milky Way is moving towards the great attractor. Also, of more immediate concern, Andromeda is about to hit us in a mere 5 billion years. So, just to illustrate our current situation, we got the Milky Way, which has in between, definitely doesn't point that way, which has in between 3 to 4 spiral arms. Let's just put an extra little half spiral arm there. And here's Andromeda, the galaxy that's about twice as big as us. It's going towards us. We're going towards it. But the two of us together are overall moving this way. Here's why we don't know what's going on this way. Because the Earth is here. It's off the Orion spur on the Sagittarius spiral arm or whatever it is. As y'all can definitely tell by this point in the class, I'm not too into memorizing names or nomenclature. But whatever, the Earth is here. Whatever the great attractor is on the other side of the center of the galaxy from us. The center of the galaxy is really hard to see through. So, we don't know what's over there. But at the same time, we do. The great attractor has got to be a massive supercluster of galaxies. We can't see it, so astronomers won't say they know that's what it is. But we can't imagine what else it could be. So, as far as I'm concerned, that's almost certainly what the great attractor is. We're being pulled that way, but I think that before we get there, dark energy will have its way with the universe and we'll be separated from it by enough distance that it'll cease to be part of our universe. And for more on that, wait until Unit 13, which will probably be recorded and given as extra credit. Other questions over anything? Okay. So the other planets move more slowly because they feel a weaker gravitational attraction from the sun. Also, they have greater distance to travel, which means that they take a really long time to go around the sun. And also, you can tell how old these slides I stole are by the fact that Pluto is included as a planet. Pluto's not a planet. That's that. So the sun has a certain amount of gravity. That gravity has to be spread out equally around a sphere surrounding it. The further you go out, the bigger the sphere, the weaker gravity is. Surface area of a sphere goes as 4 pi r squared, but forget about the 4 pi part. This is astronomy. We don't care about little numbers like that. We just go with proportions. The force of gravity gets weakened as a function of the distance squared. So I'm going to do a brief practice with gravity weakening, not nearly as much as I normally would. But we're going to have to loop back through and do this next week. I went through this with you all before. 1 dimension, 2 dimensions, like a flat sheet, or a piece of wrapping paper wrapped around an object, and 3 dimensions, like a volume, like an actual physical object that exists in our universe. Gravity weakens according to an area. By which I mean it weakens as distance times distance. Or if you're particularly mathematically inclined, distance squared. So let's talk about Earth-Moon attraction. Let's say the moon's distance doubles. That means the force of gravity goes from equivalent of 1 to 1/4. The moon's distance tripled. We go from a force of what it is now to 1/9 of what it is now. If the moon got twice as close, then the force would go from what it is now to 4. If it got 4 times closer, it would go from what it is now to 16 times stronger. So distance really matters in terms of gravitational force. And hopefully, when when you all next join this class, I'll have a whole bunch of these sorts of problems written up on the whiteboard, and you'll get a chance to go at them, and I will follow up and see how people did. Moving on. So this is for the more sciencey amongst you. This is the actual physical law. G is some kind of weird constant. M1 is the mass of one of the objects. M2 is the mass of the other object. And R is the distance between them. Double the distance, quarter the force. Half the distance, increase the force by 4 times. If the apple was hanging off a tree located on the surface of the earth, the value of R would not be 0. The value of R would be the radius of the earth, plus the height of the apple. When you use this law, you always measure in between the center of both objects. Here's the reason why. You're not feeling the force of gravity from the entire earth at once, but rather from each individual fragment of the earth. Together, they add up to the total force of gravity from the earth. The average position of these individual fragments is the center of mass, i.e. the center of the earth. Which is why when you use that law, R is always from the center of object 1 to the center of object 2. No matter what, as long as they're spherically symmetric, which very big objects are forced to be due to the force of gravity, making very large masses collapse into spheres. So larger masses produce greater forces, and the force is inversely proportional to the square of the distance between the masses. Larger distances produce smaller forces. The further away you are from the sun, the less you feel the sun's gravity. Double the mass of one object, the total gravitational force is doubled in strength. Double the distance between the objects, the total gravitational force is only a quarter as strong. In reality, the body being orbited does move too, and none of these applets work anymore, so I'm going to have to do this for you on the chalkboard. And excuse my poor drawing. Everybody looking at the chalkboard?
Yes.
Great. So I never remember what the astronomical symbol of Jupiter is. I think it looks something like this. I'm just going to put a J in the middle so you know it's Jupiter. And here's the sun. Jupiter goes around the sun counterclockwise, like every major planet. As Jupiter goes around the sun goes like this. It physically gets pulled around by Jupiter. This is one of the big ways we detect planets outside of our own solar system. Really massive planets will pull their stars around in little circles. And Jupiter does the same thing for the sun. So when Jupiter is here, this would be about when the sun, where the sun is. When Jupiter is here, this would be about where the sun is. When Jupiter is here, This would be about where the sun is. So even in our own modest solar system, a star can get pulled around by the gravitational force of the planets that are orbiting it. Is there anybody who's so industrious they looked up what the actual astronomical symbol of Jupiter was? Oh well. I didn't either. Challenge problem. How many times can the volume of the moon fit inside the volume of the Earth? Try to work it out and then chat me your answer. Okay, they're giving you a distance comparison. The length of the moon is 1/4 of the length of the Earth. Or the length of the Earth is 4 times the length of the moon. But when they ask how many times can something fit, that's a volume comparison. So volume is a three-dimensional thing. It's the length times the length times the length. I've heard from 1/4 of the class. And I guess that's enough. So the length of the moon is 4 Earths. Excuse me, the length of the Earth is 4 moons. So how many times does the moon fit inside the Earth? 4 times 4 times 4, which if you feel particularly mathy, is 4 to the third. 4 times 4 is 16, times 4 is
64.
64. The moon would fill the Earth 64 times, which is appropriate because remember, it's just our crust. This is why we have such an easy time mining metals, because our crust is in orbit around us. There's another one I'm going to throw you at some point in the quiz. So if it is not clear and you need help, either meet me an hour before class or set up a Zoom. All right. Conservation of angular momentum. This doesn't really fit here, but doesn't really fit anywhere. When a spinning figure skater brings in his or her arms, the distance from their spin center is smaller, so their speed increases. When their arms are out, the distance from the spin center is greater, so they slow down. So as you know, the solar system is extremely flat. All of the planets are in a plane that is more straight than your average dinner plate. Why would that be? This is not a full explanation, but by way of starting the explanation, let's look at this. Nope, that's not what I wanted. Hmm. Well, it should be one of these. Hold on. One of the Zoom screens is blocking my ability to look at the list. All right, this one. So as things move towards the center, they spin faster and faster. And this is the analogy that everybody uses, but it doesn't make it wrong. You got a big piece of pizza dough, and you start it spinning, and you toss it in the air. What happens to it?
It expands.
And what does the shape become?
Circular.
And how does the width change?
Gets thinner.
It gets thinner, it gets flatter. So the same principles that are involved in why spinning pizza dough causes it to flatten out are the same principles that are involved in why the solar system is flat. I'm not going to go much deeper into it than that, but at least now you all have an analogy to grab onto. This is why all the planets are in a flat plane. As the Earth spins, it bulges out around the equator. This is why Mauna Kea is technically further from the center of the Earth than Mount Everest, even though it isn't much above sea level. This is highly exaggerated, but let me show you basically what's happening to the Earth. There you go. Mauna Kea is closer to the equator than Everest is. And so, even though you can walk up it as a stroll, it is still technically the highest peak on the Earth as measured from the center of the planet. Not, of course, as measured as distance above sea level. So it depends on how you want to look at this. So, I don't much like this quote, but for those of you who are fans of Hitchhiker's Guide to the Galaxy, the quote would be, "Flying is the art of throwing yourself at the ground and missing." This is kind of what it's like to orbit. you shoot yourself very strongly sideways and slightly upwards, and eventually you end up in a situation where you're in free fall, but the amount that you fall is exactly equal to the amount that Earth curves away underneath you. And that's how you get in orbit. So next time you see a rocket launching, when the rocket seems to be moving sideways and not straight up, that's not your imagination. That's very much by design. If the cargo of the rocket is meant to be in orbit, that's what you have to do. Now, if the rocket were going on a moonshot, which happens very seldom, I think the Chinese most recently did it, then the motion will be much more directly upwards. So if you want a circular orbit, you launch at a certain speed, an elliptical orbit, a little faster, parabolic orbit, where it just barely escapes, faster still, or hyperbolic orbit, where it really escapes, faster still. These are things that require tremendous speeds. Okay, fire, nothing. Just hit the ground. Let's fire a little faster. Nothing. Just hit the ground. Keep in mind this velocity is entirely horizontal to the local surface. It's not up at all. Fire. Nothing. Just hit the ground. It's getting further, but it's just hitting the ground. Fire. A little further, but hits the ground. Fire. In the absence of air resistance, it achieves an orbit. Let's get a little bit bigger of an orbit. There you go. And that seems stable-ish. So we see the orbits of typical comets and asteroids compared with the planets Mercury, Venus, Earth, Mars, and Jupiter. Shown in red are the three largest comets that we typically cross paths with: Halley, Knopf, and Encke. My apologies for mispronouncing them. In blue are the four largest asteroids: Ceres, Pallas, Vesta, and Hygiena. All these things are in orbit. It would require some amount of speed to escape all of them, but it requires more speed to escape Earth than any of the ones shown except for Jupiter. How fast do you need to travel in order to escape the Earth's gravitational pull entirely? Well, there's a physics answer, and you work through it. And the answer is 25,000 miles per hour. So the speed of a normal bullet is 1,700 miles per hour. In order to really leave Earth's gravity, like Voyager did, the probe, Not like the Apollo astronauts, which did not actually have to leave Earth's gravity. Remember, the moon's in orbit around the Earth, so they're just going to the moon. But in order to actually move elsewhere in the solar system and potentially even escape it, you have to be moving much faster than a bullet, about 25 times faster. And you have to get to that speed in a matter of a few minutes. This is why blastoff is extremely uncomfortable. The acceleration you have to undergo is huge. So how much stuff is in orbit around the Earth? Probably more than you think. Let's take a look. So this is getting to be a problem. There's so much stuff out there that we're running out of space in which we could put more stuff. Let's zoom out a bit. Yeah. Near Earth orbit is full of junk. So much junk that the International Space Station has to do course corrections several times a day in order to avoid hitting it. Eventually, unless we deal with it, there's going to be so much junk out there that we really can't leave the planet Earth safely. So the European Space Agency has its first mission up there to deal with this junk. They basically launched a mobile satellite with a net, and the thing's job is to collect junk until the net is full, and then to just deorbit and hit the Earth's atmosphere at a glancing angle so that everything burns up. You do that 100 times, and space starts to clear out. See, there's a bunch of chats coming through, which is delightful. Let me see if I can get to them. So, Wally, is that you? I don't know. I assume not. I'm not sure what Wally is in this context. And
Sorry, it's the opening sequence of a movie.
Oh, okay. Which movie?
It's called Wall-E, and it has to do with like how humans destroy the Earth and they have to escape into space, but the Earth is surrounded by old satellites and debris.
Oh, I get that. My kids aren't old enough for me to watch that with them yet. Are a lot of the stars we see in our sky just satellites? No. No, satellites are dark. There has to be just the perfect angle in between the sun and your particular spot on the Earth to see them. There's an app for your phone that will let you look at the International Space Station when it's available to look at. The ISS is super reflective, much more reflective than any random space junk that's flying around the sky. And you can still see it only very occasionally. So, no, this stuff is dark. It's dark, dark, dark. You don't see it when you look up. It's dark and tiny. That doesn't mean it isn't dangerous, because it's also moving fast. I don't have enough time to do vector addition. That's another thing we're going to have to pick up next week. Sorry about the long delay starting class. All right, briefly Lagrange points. Without getting too much into the physics of it, whenever you have a planet orbiting a sun or a moon orbiting a planet, as long as there's only two biggish objects involved, there are 5 stable-ish spots that you can hang out at. So only L4 and L5 are actually stable, If you're at L1, L2, or L3, then you're going to have to expend a little bit of energy to stay there, but not as much if you're just out randomly in outer space. Consequently, these represent great spots to put objects. For example, in the Jupiter-Sun system, the mass of the asteroids hanging out at L4 and L5 for Jupiter is about the same as the total mass of the asteroids in the asteroid belt. That's how much junk Jupiter has collected in its L4 and L5. We've got a little bit of stuff in the Earth-Sun system at L4 and L5. And as far as the Earth-Moon system goes, there's no Lagrange point at which we haven't planted a satellite, or two, or three, or more, to do various different types of observations. Just represent great places to park and do stuff without having to expend energy all the time to keep up your relative position to the blue thing, whatever the blue thing is, be it the moon or the Earth or Jupiter or whatever. So the International Space Station orbits the Earth at 17,000 miles per hour in a nearly circular orbit. If the ISS has to feel the Earth's gravitational pull to keep it in a circular orbit, then why do astronauts float? They float because they're in free fall. They float for the same reason that you would float if you were hanging out in an elevator and the elevator cord suddenly failed. Yay, you're falling towards your death, but you do get to float. While in space, astronauts are falling freely, so they experience weightlessness. There's a link to another applet that no longer works. Moving on. The ISS is a man-made satellite of the Earth. The moon is a presumably not man-made satellite of the Earth, though I've read at least one science fiction book that posits otherwise. The Earth is a satellite of the sun. Anything that orbits anything else counts as a satellite. So this next segment is about the moon and its relationship with the Earth. I'd like to take a few minutes and brainstorm all the ways you can think of that the moon affects the Earth. So this is going to happen quite a bit differently with a remote class than it would with an in-person class, but just talk to the room. Let me set a timer for 2 minutes. Say whatever you'd like to say.
Tides.
Tides. I agree. Tides. Tides are a big deal. The moon causes tides. We're all agreed.
It affects our gravity.
It affects the gravity of the Earth somehow. It stabilizes our tilt. That's one big thing. Otherwise, our seasons would be all wackadoodle, even more than they are now.
It serves as a calendar, or it did for like thousands of years.
I mean, it still does for lots and lots and lots of cultures. The Muslims go by the lunar calendar and they do just fine. Well, more or less. I mean, I wouldn't want to be celebrating Ramadan above the Arctic Circle. It's kind of tough if the sun never rises. Any other ideas? I haven't seen anything in the chat screen yet.
Moon?
That's one of our shows. Would it affect animal habits?
Kind of. I mean, the light that the moon emits on the Earth is pretty dramatic. it really affects how stealthily you can move around at night. "25 seconds left." All right, I'm gonna hit stop. Let's go through everything I thought of. Brightness. Moon phases make a tremendous difference in how bright the night is, away from artificial light. Keywords is away from artificial light. Like, this has nothing to do with our modern world. San Francisco's bright, much brighter than the moon is when you're walking around on the streets of San Francisco. But the full moon is 40 times brighter than everything else in the night sky combined. A person with good eyes can read by the light of a full moon. A person hiding in shadows during the full moon is basically invisible because there's only one source of light. The shadows of whatever they're hiding behind is absolute and dark. So if you're just standing there in the shadow, your concealment is basically total. Alternately, during a totally new moon, humans have a hard time seeing features of motion at all using visible light. Like at night, when the moon is new, aka not up at all, it's really hard to see. History. In May 28th, 1585 BCE, the Ionian Islands were warring with the Lydians and the Medes. No worries if you have no idea who any of these people are. Thales, by the way of Miletus, had told the Ionians that an eclipse was coming, and they used this to gain a big advantage in the war by attacking during the eclipse, which vastly disoriented their enemies. And as I mentioned before, I have nothing good to say about Christopher Columbus. Feel free to report me to Napa Valley College. But in 1503, on his fourth and last voyage, Columbus ended up stranded on Jamaica, and after 6 months, the natives were just sick of him. Columbus had an almanac that predicted the lunar eclipse, and he successfully put one over on the natives by saying that his god had become angry and wanted them to continue feeding him and his men, or else he'd take the moon away. And then, of course, eclipse, and Columbus didn't die. There. He did die eventually. 1503. The moon also shields us somewhat. Looking between these two pictures, which side do you think faces away from the Earth constantly? The left side or the right side?
The right.
The right.
It doesn't shield us that much. I don't want to make it seem like the moon protects the Earth absolutely, but it's definitely absorbed a few major impacts for us. But large surfaces of the Earth would look like this too if it weren't for the fact that we have weather and a biosphere and wind and an atmosphere and stuff like that. Like, we have been bombarded far more than the moon has been bombarded. It just doesn't matter here because the planet's alive and still hot and has an atmosphere and rain. All those craters on Earth have been washed away, including the one that killed the dinosaurs. But there are certain telltale gives that it happened. Culture. In most cultures, the moon's associated in one way or another with the presence of gods or rituals. We like to see shapes in the moon, which is called, I'm going to mangle this word, periodelia. There's a mouse that's visible in the northern hemisphere, but it's upside down in the southern hemisphere. So different cultures tend to observe different shapes depending on their latitude. But finally, most relevantly to this class, gravity. we need to talk about the interaction the moon has with us and we with the moon through gravity. Specifically, we're going to be talking tides. The tidal force is the difference between the total average force an object exerts as a whole and the force at any one given point. Tides have a big influence on life on this planet. And in order to elucidate things, let me draw you a couple other pictures. So here's the Earth, and here's the moon. The moon tugs more strongly on the side of the Earth that's closest to it. And it tugs about medium strength on the side of the Earth on the middle of the Earth. And it tugs by a relatively small amount on the side of the Earth that is furthest from it. That is what tides are. Well, let's look at the consequence of them. This is a side-by-side comparison of the Bay of Fundy in Canada at high and low tides. So let's see what that looks like. High tide, low tide. There we go. So, for reasons I'm going to get into in a bit, tides are greatly accentuated by how close two bodies are to each other. Out in the open ocean, they almost don't matter. It's a difference of a few feet. But when you have two bodies of water that are close to each other, it is a significant difference. That big a difference. Even in California, there's a backpacking trail I'd very much like to do someday, where you gotta pay attention to the tide tables in order to not get drowned, because you're walking along the ocean. Oh, hold on.
New Brunswick's Bay of Fundy coastline. A journey along one of the world's most famous
Am I back?
I think so.
Yes.
I mean, if you heard me say, am I back, then I'm back. At what point did I disappear? Did you all see the animation of the tides going in and out?
Once a different video started playing, that's when it cut out. But I think we all saw the video of the little animation of the tides.
The Bay of Fundy? Yeah. Alright. Well, let's continue and see how the internet gods treat us. So, the moon exerts a gravitational force on the Earth. This force is slightly stronger on the side of the Earth closer to the moon, and it's weaker on the side of the Earth furthest from the moon. And it's about in the middle, in between the two, in the middle of the Earth. So every fragment of the Earth feels a unique gravitational pull from the moon. R is longer on the side of the Earth furthest from the moon, so the gravitational pull is about 7% weaker on that side. Keep in mind that this is an explanation for a planet that has a rocky core and has water all around the outer surface. After we go through this reasoning, we're going to look at the more complicated situation that is the actual Earth. Wait, am I still recording? Hold on. I'm still recording. Great. Also, as I said before, tides in the open ocean are quite mild. Large tidal differences happen when water is squeezed in between land masses and the sea floor is shallow. So let's talk about the idealized situation. If the Earth were all water, the moon exerts a gravitational force on the Earth, and the Earth has a response where the water closest to the moon gets pulled towards the moon, and so there's a bulge. And what's harder to explain is why there's a bulge on the other side. That is occurring because the middle of the Earth is being pulled towards the moon at a greater acceleration than the water on the far side of the Earth is being pulled towards the moon. So that bulge is basically created because the center of the Earth is rushing away from it. Net result, the side of the Earth that is closest to the moon gets a bulge. The side of the Earth that is furthest from the moon gets a bulge. And the whole Earth just turns, but the bulge stays constant with respect to the moon. It's always pointing towards the moon or away from the moon. So we get high tides and low tides. So, where in the sky should the moon be for the lowest possible tide? Should the moon be either just rising or just setting, directly above, on the other side of the planet, just setting, or either directly above or on the other side of the planet? I'd like to ask you all to take a screen capture of this page, and then I'm going to go one back. Everybody who needs it, got it?
Yep.
So, where would the moon have to be? Okay, I'm getting an assortment of answers. Let's go back to looking at this image. The places where the tide is low are the spots in which the moon is just rising or just setting. Remember, things rise and set when they move in and out of your field of view. When the moon is directly overhead, the tides should be at their strongest. So the answer is A. The moon needs to be either just rising or just setting. So this is such a good discussion. We do it in class. It's just not going to be that way on Zoom. I'd like you to think about what features the Earth has that might complicate this behavior that we've studied thus far. I'm going to go take a quick restroom break. I don't think we're actually going to finish this unit, but I'll be right back. I'd like to encourage you all to talk to each other. I won't even be in the room. Just say stuff.
Wouldn't weather affect it?
I think we should also consider landmass as well.
Okay, what'd y'all come to as far as conclusions go? What makes the Earth different than these idealized situations? Let me check the chat. Yes, large mountain formations. Look, we got a bunch of continents in the way of the ocean. So that's a problem. Complicated water systems, solutions splash in ways that are much more complicated than what they would do if we didn't have two large continental systems in their way. We got North and South America, and we got Eurasia / Africa. And that means you can't just assume that when the moon is directly overhead, the tide is going to be high. And when the moon is setting, the tide is going to be low. In fact, the tide tables look more like this. Notice how they kind of revolve around. It's because they're physically hitting the continents and reflecting backwards. The moon's important, but so is the fact that there's gigantic land masses in the way. So this is why things like tide tables exist. And by the way, inside of a water system that's as complicated as the bay, it gets even harder to understand than this. So if you want to go to Point Reyes at low tide, look up your tide tables. Don't just assume all will be well if the moon is directly overhead. Tidal forces affect solid bodies as well. The oceans are liquids, and they easily respond to tidal forces. However, the solid Earth itself also feels tidal forces. The difference between the actual force at each point and the average force is called the tidal force. Remember, the moon's pulling harder in this situation, in this picture, on Africa than it is on the middle of the Pacific, and it's pulling about a medium amount on the center of the Earth. This results in the solid Earth being stretched about 1 foot in between high tides and low tides. So go ahead, sit in your chair, wait 12 hours. Your average height relative to the center of the Earth is going to change by about 1 foot. Now, you're not going to feel it. It's very slow, and it's spread across the entire Earth, but it still happens. Friction from the stretching causes the Earth to gradually lose energy, and thus the rotation is gradually slowing down. You all remember, I'm sure, how the moon rotates at the exact same rate that it orbits. It always faces us with the same side. It would like to do the same thing to us. When the dinosaurs all got, I don't want to say murdered, but, accidentally killed by the cosmos, a day on Earth was the equivalent of 23 current hours. When the moon was first knocked off the Earth, it seems like the length of a day on Earth would have been about 10 total hours. So the day on Earth is constantly lengthening, and it's due to the moon. The moon is slowing us down. It would like to tidally lock us the exact same way we've tidally locked it, but fortunately or unfortunately, the sun is going to swell up and destroy us before that can happen. But at present, every day is slower by 1.7 milliseconds. The day was 23 hours long when the dinosaurs were around. Now it's 24 hours long. Of course, the moon feels stronger tidal forces from the Earth. It doesn't have tidal forces that vary by the hour because it's just phase locked. It's permanently deformed. It's about 65 feet wider than it is tall. How is tidal locking achieved? Well, the strong gravitational force on the near side of the bulge tends to slow the satellite's rotation until the rotation lines up with its orbit. The sun exerts tidal forces as well. The sun falls on the Earth about 177 times more than the moon pulls on the Earth, but the sun is much further away. So the difference between the sun's forces on the near side of the Earth to the sun and the far side of the Earth to the sun is much less than the difference between the moon's force on the Earth and between the near side of the Earth towards the moon and the far side of the Earth towards the moon. So when the moon and the sun are aligned, or anti-aligned, you get super strong tides. When the moon and the sun are at perpendicular angles, you get really weak tides. And this applet actually works. So let's switch to it. I now see somebody really enjoying a slice of pizza, which makes me hungry. Oh, great. I launched this applet, but it appears to have crashed. So enough of that. I'll try to have it up for next class. So what phases of the moon give us the highest tide? The answer is the full moon and the new moon both give us super high tides. Half moons give us the weakest tides. And what phase of the moon gives us the lowest tides? It's not a half moon, because half moons give us very anemic tides, both high and low. It's still the full and the new moon that give the very highest tides and the very lowest tides. See, when the sun and the moon are aligned, either in full moon or new moon, the gravitational forces align, and you get super strong tides. When the moon is in its half moon phase, the two of them are working at cross purposes, and the tides are just kind of in between. Not a lot of big difference between low tide and high tide. So again, consult your tide tables. But if you want to go tide pooling, if you want to see the maximum amount of weird ocean stuff exposed to you, go in the new moon or the full moon. That's when the water is going to both be extra high and extra low, depending upon the time of day. Final topic, resonances. Resonances occur whenever systems get in sync with each other in their environment. They can be destructive. Hold on, Zoom is not cooperating with me. They can be destructive, like this. So that's a destructive resonance. Here's another one. This is why Roman legionnaires and, for that matter, American GIs and every other professional army break stride when they walk across bridges. So normally an army marches. When you go across a bridge, you don't march. You deliberately step out of sync because you don't want to introduce an inadvertent resonance. the bridge eventually collapses, I guess around here. As I'm sure you can understand, people were very reluctant to leave their cars. But nobody died. There was even a dog that managed to walk off the bridge.
Girl.
Indeed. Residences can also be constructive. Look at all these metronomes that start out of sync. We are not watching this whole video. Just take my word for it. There is no human interference. Eventually you just get to. And I built that demo. It really works. In astronomy, resonances tend to be achieved via gravity. And also, much less pleasantly, collisions. Here is the most famous resonant solar system that I know of.
Scientific community, the public, you had 7 Earth-sized planets, several of which might have the right temperature to host liquid water, prime targets for the search for life outside the solar system. So what really captured our attention was when they tried to simulate the system, they found that it just fell apart. Planets started colliding with each other on really short times. And what are the chances that we would catch the system at this very special time right before destruction? It seems more likely that there's something more going on, something that's keeping the system stable. So the additional key piece of information here is actually when you look at how long each planet takes to go around the central star. Those orbital periods, they form an incredibly precise progression. For every 2 orbits of the outermost planet, the next one in does 3, the next one in after that does 4, then 6, 9, 15, 24. It's just like clockwork. We don't see that long a so-called resonant chain in any other planetary system that we know. When we tune that precisely, we can get these systems to survive for as long as we can possibly simulate them on a supercomputing cluster. So it really seems that it's this really remarkable orbital configuration that allows the system to survive long enough for us to see it today. But how am I going to communicate this with people? And then one day, Matt Russo, he knocked on my door and he said,
"Can you help me out? Do you have any simulations of the TRAPPIST-1 system I could use?"
And I said, "Well, I have thousands. How many do you want?"
So the thing that stuck out to me most about the TRAPPIST-1 system was this amazing pattern of resonances, how each planet's orbit is a simple ratio of its neighbors. And I realized that that's the exact same thing that makes music sound good and that makes it rhythmic. So we simulated the system. We scaled their orbital frequencies into the human hearing range. I made it play a note for every time a planet transits in front of the star. This may sound like a remarkable coincidence, but it turns out that the system was tuned this way early on when it was evolving. Then, we added a drumbeat for every time a planet passes its neighbor. The star's brightness data into sound and included it for a little more flair. It's kind of funny because most planetary systems are like bands of amateur musicians. They're all playing parts, but at different speeds. TRAPPIST-1 is different though. It's like a supergroup where all 7 members are synchronizing their parts in nearly perfect time.
See, somehow.
Alright, so I don't think that music sounds particularly good, but that wasn't really the point, I guess. The point is that there was a resonance that was constructive, and it was achieved by gravity. So now you're done with Unit 4, and I owe you guys. I owe you grading. Unit 4 will be pushed out. I need to do the math. I'll probably record an additional session tomorrow at work. And I will go through and actually grade all the material that's been submitted. Sorry. Then maybe I'll launch the quiz. Or maybe I'll work on it a little more. I don't even know. When I do launch the quiz, I'll send an announcement and it'll be open for 48 hours or whatever. I was doing demos for a Cal professor that said, "Don't cheat, I'll cash you." Only much more sassy than that. And I was like, that guy's great. But the fact of the matter is, if you cheat, I probably can't catch you. So, all I can do is ask you not to cheat. And welcome to the coronavirus era. As a classroom instructor, I think I have really good test protocols. I walk around, I stare at people, I see if they're looking at their cell phone, I write numbers on the desks, and I hand out tests or quizzes to people as they come in and they have to sit in those spots. All the rigmarole. But now that we're in this phase, I can't really do any of that. And I'm so stressed for time, I'm not going to develop new techniques. So please don't cheat, is all I can say. Please. I'd really appreciate it if you just looked at the very simple tests that I've written and thought about the lessons I've been giving. Homework 4 will be due definitely later the next Monday. If I get the time at Cal on Tuesday to record all the extra math practice that I had to skip tonight, then I guess I'll make it due on Tuesday or Wednesday. But y'all should know I'm not a hard person to talk an extension out of. One student emails me and says, I'm having a hard time getting this stuff done, and explains why. I just bumped the date out. So, probably next Tuesday. Maybe later.
For the homework assignments, you have them so they're locked for, or at least for me, for Unit 3 and Unit 4, they're locked, so I can't submit anything.
That sounds like something I need to fix right now. Let's see.
It has the due dates from set to like dates in 2020, so they're all like past due.
Oh, come on. I'm not saying that to you. I'm saying that because I can't actually log into Canvas. As usual, most times. All right, Unit 1 homework was due February 2nd. Unit 2 homework was due February 23rd. Seems about right. Unit 3 homework was due September 29th, 2020. That's not okay. Let's fix it. So I'll give you all until March 16th to get Unit 3 done, because clearly that's my bad. If I can actually do that. All right, March 16th, which means you have additional class period to ask questions. That's for Unit 4. Well, I don't know exactly when I'm going to finish everything I was able to get today, but it certainly shouldn't be due October 13th, 2020. So let's tentatively put it for, I guess, March 11th. That'll give you time to ask questions in, wait, no, March 17th. Sorry. I'll give you time to ask questions in the next class and a couple days to work on it after that. Other questions? I mean, the website is awful. Canvas is awful. It's a travesty. I don't know. So on UC Berkeley campus, the internet fails all the time nowadays because the IP people just don't care to fix it because there's nobody on campus. It's just an endemic collapse of education all across the board. Yeah, both of them are due on the 16th, I guess, unless somebody asks me to make them due later. I don't know. So somebody just asked me, how long do you think it will take to put the missing class recordings on YouTube? They're always available on Canvas. I have like 7 recorded demo videos I still have to put up on the UC Berkeley demo website. That is mildly more of a priority than putting the recordings of Astro classes on YouTube, because y'all can, in theory, see all these, right? Is there anybody who's having huge difficulties just looking at previous recordings? Just go to go to Tech Zoom Connect or whatever it's called nowadays and click on the recorded classes tab and you should have it. Whether or not it's up on YouTube. But I will eventually get them downloaded and put them up on YouTube. It's just, I'm sorry, and no student wants to hear this from their teachers, but I'm just busy. It's not an easy semester. I find the pandemic has either reduced most people's work down to almost zero or increased it up to several thousand%. And I'm closer to the second category than I am to the first. So you all have a way of seeing them before they're on YouTube and just use that. And I'll get them up on YouTube when I can. Okay, somebody just said they'll need some more time. Great. Shoot me an email. Explain your circumstances. One thing I do understand about Canvas is I can give individual extensions based on time to single students or to the entire class. We'll just see how people respond and I'll get back to you. But anybody who needs more time, up to a week more is fine. And now it's 10. So I'm always accessible via email, give or take. So shoot me a message if you need me. I'm out. It's late for me as well as you. Everybody take care. Be safe. And again, I don't want to be political, but wear a mask. Wash your hands. Pandemic's not over yet. Don't get sick.
Thanks for reminding people of that.
You're welcome.
Have a great night, though.